We can now combine all the results that we've been working on over the past few videos to determine the molecular orbital energies for our system H2+. So I'll remind you that we defined the molecular orbitals as linear combinations of atomic orbitals in the following way, where we have as a normalization constant 1 over 2 times the square root, 1 over the square root of 2 times 1 plus or minus s. And then we have two atomic orbitals here on atom A and atom B. We're going to actually, in this case, go ahead and let them be both equal to the 1s orbital on each of the hydrogen atoms. And we've defined the Coulomb integral and the exchange integral as shown down here, Coulomb and exchange, basically as combinations of 1 over the distance between the protons r and these integrals over the atomic orbitals and their distance relative to the other proton. So how will we combine all of this together? Well, remember that our energy of these molecular orbitals would be given by psi plus or minus h psi plus or minus divided by their overlap integral, psi plus or minus, the inner product. And now we can write this out, as we have in previous video, as 2 times E sub 1s times 1 plus or minus s plus j plus or minus k, where these are the two integrals over here, the Coulomb and exchange integrals. So these are key elements in determining the energy of our overall molecular orbital. Now this is going to be divided by this overlap function, so it's 2 times 1 plus or minus s. Now you'll notice that this 2 plus or minus 1s is the same as what's up here, with the exception, with the addition of this energy of the 1s orbital. And then we'll have, and this should have been a 2 in front of this, we'll have the 2's cancel, and we'll end up with this quantity of j plus or minus k divided by 1 plus or minus s. Now, what we're basically doing is we're saying that the energies of the molecular orbitals can be written relative to the energy of the 1s orbitals on the individual atoms. So what we're going to really care about is a quantity that is the difference between these. So I'll call it delta E plus or minus, which is just going to be E plus or minus the energy of the 1s orbital. This is where it would be if we just had a single atom. So this is going to tell us something about the binding energy of the molecular ion H2+. So when we write that explicitly down here, we'll have delta E plus or minus is simply equal to j plus or minus k divided by 1 plus or minus s. All right, so how do we interpret all of this stuff? How do we make sense out of this? Well, there's a couple of things we can do. One, these Coulomb and exchange integrals for the 1s orbital can be explicitly evaluated. And in fact, what we would get when we do that is the Coulomb integral would be equal to e to the minus 2r times 1 plus 1 over r. The exchange integral, as a function of r, would be equal to s over r minus e to the minus r times 1 plus r. All right, and I'll remind you that earlier we had found that the overlap integral could be written in terms of the 1s, for the 1s orbitals, in terms of this distance between the nuclei as 1 plus r plus 1/3 r squared all times e to the minus r. Okay, so we've seen what this function looks like. It's simply a decaying function that kind of comes down gradually as we go to larger and larger r. What about these two functions? Well, these exponentials always have to be positive numbers, okay? They're just the way they're defined. All right, what about the stuff in parentheses? Well, for the j integral, this stuff in parentheses is 1 plus 1 over r. r is a positive number, so all of this represents positive quantities. So j is a number that has to be greater than 0. And as it goes to 0, it's going to blow up because this term is going to get really large. Okay, and this term is going to go to 1, so I'll have 1 divided by some really small number when we go to 0. Okay, what about k? Well, in this case, we have a term here that's going to blow up as we go to 0, so it's going to be very large and positive. But then we have another term out here as r goes out, as r gets larger. This term will eventually be larger in magnitude than this term, but it's got a negative sign in front of it, and everything over here is positive. So as r increases, this term will become less than 0. So k has parts that are both greater than 0 and less than 0. Greater than 0 when r is very small, less than 0 when r is larger. And the Coulomb integral is always greater than 0, but I'll note that as r gets very large, this term is going to get very small. So we could actually draw these terms, and maybe that's a good idea. So for the Coulomb integral, and I'll put 0 here, for the Coulomb integral we'll have something that's very large and kind of decays to 0. So this is j. For k, we're going to have something that comes down, becomes negative, and stays negative, though it also approaches 0 as it gets very large. So this is what these two functions look like for the 1s orbital as we get larger. So you can see that what we have is now an opportunity for their sum or their difference to have a particular sign. And in particular, j plus k at large enough r can go to a number that's less than 0. J minus k, on the other hand, is always going to be a number that is greater than 0, as it turns out. So, in fact, when we draw these things, remember we've got e to the plus or minus is j plus or minus k in the numerator divided by 1 plus or minus s. Well, s is always less than or equal to 1, so in fact 1 plus or minus s is always going to be, generally speaking, less than 1, but it's going to be greater than 0. So in this case we have a positive number in the denominator and a number in the numerator that can either be positive or negative. And when we draw this out, what we'll end up with is a plot that looks like this. And again, I'll put 0 here in the middle somewhere. And we find that we have one of the curves comes down like this, and one of the curves comes down like this. And the term that goes below 0 is actually the plus sign of this linear combination, and the one that stays above 0 is the minus sign. So in other words, this plus sign basically tells us that this energy of the molecular orbital can become more stable at certain energies than it would be for separate atoms, which represents the 0 in energy here. The 0 in energy is when our delta, I should have put deltas here, this delta E plus or minus is equal to 1s. So this 0 in energy represents separate atoms for the two hydrogens. All right, so this is a very interesting result. It basically tells us that our plus combination is one that results in a more stable form. So we're going to call this a bonding orbital. It's one where these two find a lower energy when they are bound together. The minus combination is something we'll relate to an anti-bonding orbital. Where the two never achieve, unless they get to an infinite separation, they never achieve an energy as low as having the separated atoms. Okay, so when we draw these things out, the bonding orbital, since it's a plus combination, you'll remember that we drew a picture of this in an earlier video, where this thing came up and it looked something like this. So this is what that orbital might look like. What about the antibonding orbital? Well, it's a minus combination. It's Phi A minus Phi B. So in this case, if we drew this same kind of picture, and if this is A and this is B, okay, the A part's going to be positive. The B part, though, is going to be negative. So when we're in between these two, we have to have something that comes down and eventually meets something like that. And I've exaggerated the nonlinearity of this. But what you can see from this is that in order for it to go from this point to this point, it had to pass through a place where the wave function was 0. So in other words, there is a node, and that node exists in between the two nuclei of that atom. So this is what is going to characterize an antibonding orbital in this case. So what we've learned from this very simple H2 plus example is the fact that a certain linear combination, the plus linear combination, which represents a bonding orbital, results in an energy that is lower than it is for the separate atoms, whereas the antibonding case results in an energy that is above the separate atom energy.